Chapter 11 Eigenvalues and Eigenvectors Section 5 Geometric meaning of eigenvectors and eigenvalues. In this lecture, we will explore the geometric meaning of eigenvectors and eigenvalues. Through intuitive examples and matrix types, you will learn how these concepts explain stretching, shrinking, and direction-preserving properties of linear transformation in two-dimensional space. If you are looking for a structured path to master linear algebra from beginner to advanced, I have compiled these lessons into a book on Amazon. The link is in the description. Now, let's get started. Eigenvectors are defined for a specific matrix. Let's recap the definition of eigenvectors and eigenvalues. For a matrix A that represents a linear transformation, a vector v and a scalar lambda satisfy this equation. The important point here is that an eigenvector v is a special vector that maintains the same direction even after transformation by A. However, while the direction is preserved, its length may change. The eigenvalue lambda is a scalar that indicates how much the eigenvector is stretched or shrunk under the transformation. In short, eigenvectors are special vectors that do not change their direction after transformation. Eigenvalues indicate how much the vector is stretched or shrunk. Geometrically, they serve as an important tool to represent the main directions of transformation in space. A matrix A generally represents transformations such as rotation, scaling, and shear. Normally, vectors change direction after transformation by matrix, but eigenvectors are special vectors that do not change direction. Let's see an example of two-dimensional space. Consider this matrix A. When calculating the eigenvalues and eigenvectors of matrix A, we obtain these eigenvalues and eigenvectors. As to the pair of v1 and lambda 1, the vector v1 remains the same direction after transformation and stretches by a factor of 3. As to the pair of v2 and lambda 2, the vector v2 also retains its direction and remains unchanged, that is, scaled by 1. Thus, eigenvectors indicate axes that do not change direction before and after transformation, while the eigenvalues determine the amount of stretching or shrinking along those axes. A matrix generally represents transformations such as rotation, scaling, and shear. In such cases, the direction of a vector may change. However, vectors along the eigenvector directions do not change their orientation. They only stretch or shrink. A rotation matrix rotates vectors, which means the direction of any vector is completely changed. Therefore, a rotation matrix generally does not have real eigenvectors. A shear matrix skews a shape by stretching it diagonally, so only certain vectors maintain their original direction after transformation. Thus, a shear matrix typically has only one eigenvector, or, in some cases, no eigenvectors at all. A diagonal matrix scales each component independently, so the unit vectors along each coordinate axis become eigenvectors. Let's examine each of these cases in detail. A rotation matrix has the characteristics that it changes the direction of all vectors. Thus, it does not have real eigenvectors. For example, A two-dimensional rotation matrix that rotates a vector by an angle theta can be expressed in this way. To solve this matrix, we derive the eigenvalue equation. Solving this equation gives the eigenvalues. Since the solutions are complex numbers, the eigenvalues are also complex. Therefore, real eigenvectors do not exist. In conclusion, it has been demonstrated that a rotation matrix does not have real eigenvectors. Shear transformation is a type of transformation that shifts the components of a vector in one axis direction along another axis. As an example of a shear matrix, consider this matrix S. This matrix S represents a shear transformation that shifts the x component in the y direction. For example, when k equals 1, applying this matrix to a vector xy results in this transformation. In this transformation, the direction of a general vector changes. However, certain vectors maintain their direction. These are the eigenvectors. Now, let's find the eigenvectors of a shear matrix. The eigenvalue equation is given by this equation. Next, find the eigenvalues using the determinant equation. Let's continue with the determinant equation. Expand the determinant equation. Thus, the eigenvalue is lambda equals 1, which has multiplicity 2. The eigenvector equation is given in this way. Solving this equation for any v2, we get this equation. Thus, when k is not equal to 0, v2 equals 0, so the eigenvector is 1, 0. In a shear transformation, the direction of many vectors changes, but vectors along a specific direction, in this case the x-axis, maintain their orientation. This direction represents the eigenvector, which is an axis that is not affected by the shear transformation. A diagonal matrix is a matrix in which all elements outside the diagonal are 0. Let's consider this a diagonal matrix D. To find the eigenvectors, we consider the eigenvalue equation. Rewrite this equation explicitly for the vector v. We get this equation. Next, break this down into components. From this, we find that when x is not equal to 0, lambda equals a. And when y is not equal to 0, lambda equals b. And the corresponding eigenvectors are these vectors. Let's interpret the results geometrically. A diagonal matrix performs scaling along each coordinate axis. In this case, the eigenvector v1 is in the x-axis direction, and the corresponding eigenvalue is a. So it is stretched by a factor of a. And the eigenvector v2 is in the y-axis direction, and the corresponding eigenvalue is b. So it is stretched by a factor of b. In this way, the eigenvector of a diagonal matrix are always in the direction of the coordinate axis. The relationship between diagonal matrices and eigenvectors is useful in principal component analysis and singular value decomposition. The details will be explained in the later lectures. A symmetric matrix has the property that its eigenvectors are always orthogonal. This property is important in principal component analysis. Let me show the mathematical proof of this property. Let lambda 1 and lambda 2 be the eigenvalues of matrix A, and let the corresponding eigenvectors be v1 and v2, respectively. Consider the inner product of the eigenvectors v1 and v2. First, take the transpose of v2 and multiply both sides by it. Similarly, taking the transpose of v1 and applying it to the other eigenvalue equation. Now, let's recap the basic property of matrix transposition. For the product of matrices, this transposition property holds. Apply this property to this part. Since A is a symmetric matrix, we obtain this equation. Let's focus on this part. Vector v2 is an n by 1 column vector, so its transpose is an 1 by n vector. The matrix A is n by n matrix, and v1 is n by 1 vector. Multiplying these vectors and a matrix results in a scalar. Since the transpose of a scalar is equivalent to the original scalar, we obtain this equation. Using the property of transposition, we can rewrite the equation in this way. Let's continue with this equation. The matrix A is a symmetric matrix, so A equals its transpose. So, we can rewrite the right side in this way. Using the eigenvalue equations, we can rewrite this equation in this way. We can rewrite this equation in this way. If lambda is not equal to lambda 2, this equation holds. Thus, the eigenvectors v1 and v2 are orthogonal. Thank you for watching. Please thumbs up and subscribe to my channel.